thanks to everybody for joining. Really appreciate you joining this session. It's been a really fun conference so far. So I'm Will Masters, a faculty member in the school, and we're in person in Boston and have a chance to hear from 5 amazing students projects on food prices and unlocking the potential for retail food item prices matched to what's in the food, to food composition, and matched to all kinds of other amazing data that reveals access to healthy and sustainable diets. I won't tell you what they'll talk about. They'll go in the sequence shown: Rachel Gilbert, Jess Wallingford, Leah Costlow, Elena Martinez, and Venkat. As you can see, there's 3 of us in the room, Leah and Elena here, and then Rachel, Jess, and Ash online. Enter comments, questions, thoughts you have on the talks in the chat box, and we'll pick them up in the course of the 50 minutes that we have here together now, and we'll follow up by email. So enter your email address in the chat box if you have a question you'd like one of us to reach back to you after the session. So we'll start with Rachel.
Hi, everyone. I'm Rachel Gilbert, and I'm a PhD candidate here at the Friedman School. I'm part of the Food Prices for Nutrition project. So I'll actually start the panel off telling you a little bit generally about the project methods and metrics, and then I'll pass it off to the other panelists to tell you about our team's research on retail food prices and sustainable diets. So I'm not advancing. There we go. So since 2015, a series of projects which began here at Tufts have developed new ways of measuring physical and economic access to healthy diets. These metrics, which are known by their acronym COHD, cost and affordability of healthy diets, use retail prices matched to food composition data and nutritional requirements to identify the least expensive combinations of foods, locally available foods that are needed for health. So least cost diets, which you'll hear more about, are a really powerful framework that reveal whether inadequate diets are caused by high prices and low incomes, which lead to affordability or unaffordability, or by things like displacement of healthy foods by unhealthy foods for other reasons related to people's food preferences or time constraints. And these metrics are now being monitored at a global level through the FAO in the flagship SOFI report, which you may be familiar with, as well as through the World Bank as part of the suite of food security indicators. But we also do a lot of work to look at the variation in the cost and affordability of healthy diets at the national level. And though these types of analyses can be used to guide policy as well, whether it's agricultural policy or trade policy, efforts towards climate resilience or other things. So the reason that we track the cost of healthy diets is to focus policies and programs moving away from what's been a long-term focus on just caloric adequacy or short-term survival towards something that looks more like measuring food and nutrition security. And in our project and in the metrics that we'll talk and hear about today, we also move beyond a focus on individual nutrients towards a focus on healthy diets, which incorporate other dietary needs like diversity across food groups and so on. And something important that these methods reveal is that as you reach for these steps up in diet quality, generally speaking, there are higher costs. So it's more expensive to get higher levels of diet quality. And this least cost diet framework is really useful for distinguishing between unaffordability as a cause of poor diet quality or inability to improve diet quality and other reasons for that, such as preferences, etc. So when the next step up is unaffordable, food prices are an insurmountable barrier to better diet quality, and least cost diets help us see that. So in order to measure the cost and affordability of healthy diets, we need to define healthy diets. And many of you are probably familiar with food-based dietary guidelines, like the Dietary Guidelines for Americans, represented here by the MyPlate. Dietary guidelines have some unique strengths for monitoring least cost healthy diets in that they represent a realistic way for consumers to select a diet that's nutritionally adequate using food groups instead of thinking about just nutrients. They also represent diets that protect against nutrient deficiencies, but also protect against non-communicable diseases. And they represent culturally appropriate diets, as well as the official standard in countries that have them. So these are the policy documents that inform food assistance programs, for example. So we use food-based dietary guidelines to define healthy diets. Not all countries have them, and not all of them are readily quantified. So we need to quantify them in order to cost them in the least cost diet. And for countries that don't have food-based dietary guidelines, or for comparisons across countries done in the SOFI reports, we use something called the Healthy Diet Basket. This was developed for the SOFI and represents a globally relevant set of criteria for a healthy diet. And it is based on median amounts of each food group that are recommended across 10 national food-based dietary guidelines. And what you can see here in the table is that we have 6 food groups, and each least cost diet that's using this standard would end up with 11 items. So we have different numbers of food groups and different number of items that can be selected in each food group to ensure diversity both within and across the food groups. And then these 11 items in 6 food groups would sum to a total of 2,330 calories per person per day. So this is the standard that we use for a lot of our analyses. And then what we do to calculate least cost healthy diets is to match retail food prices and their food composition data to determine which foods are least cost in terms of their price per calorie. So then we match those to the requirements for health as determined in the food-based dietary guidelines or in the Healthy Diet Basket, and select the items that meet that criteria. So within a least cost healthy diet, food group proportions stay constant across time and space. So the share of calories from each food group remains the same. But within each food group, there's substitution between food items depending on their cost. And so least cost items can vary at each time and place. And you can see here that ultimately we end up with one cost of a healthy diet based on the cost of these 6 main food groups, for example, in the Healthy Diet Basket. You may wonder what foods are often included in a healthy diet, in a least cost healthy diet. So here we just have an example of what least cost diets look like in 3 countries based on national average prices from 2017 in the International Comparison Program data set, which I'll talk about in just a moment. So you can see that in each of these 3 countries, there's a different there's a different national cost per day. But there are, for a given food group, for example, for fruits, you can see that different items are selected in these different places. In Senegal, it was dates and mangoes for the fruits. Pakistan had bananas and coconuts. And in Italy, it was apples and bananas. So you can see the size of the category here in these images reflects the relative cost of the fruits in each country to the whole diet. But each area represents the cost to purchase 160 calories total of fruit in that diet. So this is just an example of 3 countries from the global comparisons that have been done. And across the next couple of presentations, you'll see a lot of different types of retail prices. The example I just showed you is global data from the International Comparison Program retail price data, which is collected by the World Bank once every 5 years or so. And that data set, again, provides a single national average price. So the cost of a healthy diet with these prices provides a benchmark for country work and other work, the research you'll hear about in a couple minutes. Much of the work that I do on this project is focused on working with national governments, and these subnational and temporal variation that's available in other data sets. So things like the price data sets collected by national statistical offices all over the world to monitor inflation, data from market information systems in countries. We have early warning systems, food price data, as well as things like supermarket prices and scanner data from places like Boston or other countries like Bangladesh. We have all types of food price data sets that can be used to calculate the cost of a healthy diet. And the global data set provides a benchmark for this work to look at this subnational and temporal variation. You would need these other data sets. And on this project, we spend a lot of our time also working with countries. We have 9 focus countries where we work with their national statistical offices to monitor diet costs alongside inflation using their existing food price data. And so that's a big part of this project, but what you'll hear about in the research next is how different food price data sets can be used. And I think I'll stop there because I think I've used all my time, but that's just a preview of what we do here on the project. And then I think Jess will pick up from there.
Brilliant. Yes, thank you. Thank you. And so with lightning talks, you get a flavor of things. So enter in the chat box any questions, comments. As I mentioned, we'll get back to you. And Rachel mentioned that there's this ladder of diet costs, starting with basic calorie needs, and then adding in micronutrients, and then adding in other needs, all the bioactive compounds for health, in addition to cultural and other constraints. What Jess will share is the basic foundations of this. Which if you come to the Friedman School and take the economics class, we do as exercise number 3 in the semester to look at least cost diets in terms of nutrients with some really interesting insights. So Jess, you can share the story of the Three Sisters diet.
Great, thanks. So hi everyone, I'm Jess Wallingford and I'm also a PhD candidate here at Tufts University. And as Will said, what I'll be presenting today is a component of a classroom exercise used to introduce the concept of least cost nutrient adequate diets and also linear programming. So the least cost diet is just one example of a much larger class of multi-dimensional optimization problems that give insight into decision making. And in particular, the least cost diet problem asks, what quantities of foods are needed to meet a set of dietary constraints at lowest total cost? And in 1945, George Stigler described the challenge of choosing a set of foods to meet a set of nutrient constraints at lowest total cost. He used 1939 item prices and early nutrient requirement data to guesstimate a least cost diet that included wheat flour, evaporated milk, cabbage, spinach, and dried navy beans. Then shortly after, George Dantzig developed the simplex algorithm to find an exact solution to the diet problem. And at this time, this type of computation required the work of multiple people using hand-operated desk calculators over many, many days. But now we can find Dantzig's simplex algorithm as one of the solution methods that can be selected in Excel solver add-in, and it takes only seconds to find a solution. And this is really convenient, but to those new to linear programming, this can be a bit of a black box. So we've developed a simple visual depiction of linear optimization that centers around the diet problem, and that can be used as a basis to build intuition for more complex multi-dimensional optimization models, for which we would typically use tools like Excel's solver or Stata or R. So our simplified optimization problem is designed around the three sisters, corn, beans, and squash, which have agronomic complementarities when grown together and also offer nutritional complementarities. In this example, we use local price, package, and serving size data from Stop and Shop, nutrient composition data from the USDA Food Data Central, and dietary reference intake data and an energy requirement for 19 to 30-year-old females. So we begin with just 2 foods and constraints for 2 nutrients and ask what quantities of black beans and butternut squash would be needed to meet vitamin A and iron recommendations at lowest total cost. This question can be represented by a system of linear equations listed on this slide, all of which can be drawn together on the same graph. So here we have servings per day of black beans on the x-axis and servings per day of butternut squash on the y-axis. The red lines on this graph represent micronutrient upper and lower bounds. So for example, the lower bound for iron is represented by the equation 2.51x plus 0.98y equals 18, meaning that the combination of black beans, which provides 2.51 milligrams of iron per serving, and butternut squash, which provides 0.98 milligrams of iron per serving, must supply iron in a quantity greater than or equal to 18 milligrams per day. Likewise, the selected combination of black beans and butternut squash cannot supply iron in excess of 45 milligrams. Then vitamin A in this diet is provided exclusively by butternut squash, which results in the upper and lower bounds for vitamin A being horizontal lines in red, indicating that the supply of vitamin A must be between 700 and 3,000 micrograms of retinol activity equivalents. So together, these four equations form a parallelogram or a feasible region in yellow, within which all combinations of beans and squash satisfy iron and vitamin A constraints. So the next step is to find the least cost solution among all of the possible combinations of beans and squash that fall within this feasible region. And we can do this by adding in a cost line, which is shown here as a blue solid line. So the slope of this line is given to us by the ratio of the price per serving of black beans to the price per serving of butternut squash. And the least cost solution will be the coordinates of the point touching this blue line when it has been shifted as far back towards the origin as it can be without leaving the feasible region. So with a quick visual inspection, we can see that the least cost solution occurs at point A, which is also the intersection of the equations representing the lower bounds for iron and vitamin A. And the exact quantities of beans and squash can be calculated by solving this system of two equations in two unknowns. So we can also visualize how a change in the relative prices of beans and squash could alter the slope of the cost line and change the least cost solution, as shown, for example, by the dashed blue line with a price for black beans that is 10 times higher and a new solution at point B. Our solution at point A, unfortunately, provides less than half of the calories required to maintain energy balance. So when we add in a line representing the energy requirement, shown here by the solid black line to the right of the feasible region, we can see that there's actually no combination of squash and beans that could achieve energy balance while remaining below upper bounds for both iron and vitamin A. So in order to obtain adequate energy and stay within micronutrient bounds, we need to add in an energy-dense food option. So here we add in corn flour as a third energy-dense good and ask what quantities of black beans, butternut squash, and corn would be needed to meet vitamin A, iron, and energy requirements at lowest total cost. And we could show this addition of a third food as a third axis in our graph, but it is difficult to think in 3 dimensions. So we provide a visualization of this 3 good problem in 2 dimensions. So corn brings both energy and iron. So adding in the least cost level of corn shifts both the energy constraint and the feasible region from the previous 2 food example leftwards. The original iron bounds are shown by the faint red lines, and the new shifted iron bounds are shown by the brighter red lines. Together with the original vitamin A bounds, which are not shifted in this example, these form the new shifted feasible region in yellow. And importantly, the addition of corn shifts the energy constraint shown in black far enough to the left that it now intersects with the bottom left-hand corner of the feasible region, making it possible to meet energy, iron, and vitamin A constraints. With the new least cost solution represented by point B at a total cost of $2.27 per day. So our 2 and 3 dimensional problems demonstrate basic principles that are applicable to more complex multi-dimensional optimization models, namely achieving energy balance while staying within micronutrient bounds requires both energy-dense and nutrient-dense items. The need to maintain energy balance plays a crucial role in nutrient-adequate diets, and most of the total cost of the least cost diet comes from the large quantity required of the starchy staple. The high cost of producing and distributing nutrient-rich complements makes them expensive relative to starchy staples. And finally, many people might consume less of the low-cost nutrient-rich foods like squash and beans, in this example, that would be needed for nutrient adequacy, either because their incomes are insufficient or because of other barriers in food choice that they might face, such as time constraints or cooking costs, for example. And I'll stop there. Thanks.
Fantastic. Thank you, Jess. And if you happen to remember Jess's screen of the actual portion sizes for this Three Sisters diet, the Three Sisters diet is famously used all across North and Central America by indigenous populations, all the way from here in Massachusetts to Central America, and actually all the way north where this combination of a squash and a bean growing down on the ground, with the bean climbing up the stalk of a corn plant, the legume fixing nitrogen, and the corn plant absorbing much more sunlight because it has a tall stalk. That agronomic complementarity matching this astonishingly real, that we have now discovered to be real, complementarity in the nutrients. Of course, indigenous populations didn't know about the nutrients, but they did, through trial and error, discover relative portion sizes that are pretty realistic, actually. When you look at the relative combination, the quantities, I think it was 5 servings, as it were, of the corn, and then 1 or 2 of the nutrient-rich foods. But even that little bit of nutrient-rich foods is really expensive. And so Leah is about to share, Leah Costlow will share to us the data on the world as a whole. And for the world as a whole, ever since total production and consumption began to be tracked in the 1960s by the Food and Ag Organization of the UN, we can see the degree to which total available supplies of these relatively expensive nutrient-rich foods have become available to countries.
Great. So thanks, Will. Thanks, everyone. So I'm Leah Costlow. I'm also another PhD candidate here at the Friedman School, but I'm also one of this long list of people who are collaborators on this project between us at Tufts and the Markets and Trade Division at FAO. And so I'll be talking about this work that we've been doing with the central goal of estimating the contribution of trade policy, and specifically trade barriers, to food prices and the cost of healthy diets. So to address this question, our approach is to match import costs to retail prices. And that is a complex series of things that I'll describe in more detail. And then we calculate the share of retail prices that those import costs account for. Import costs are defined as tariffs or import taxes and non-tariff measures, which includes a wide variety of policies. So for example, that could be something like food safety measures, maybe something like a limitation on antibiotics in meat, or things like compliance with technical regulations on ingredients or food labeling. And we do this analysis globally for all countries with available data, and then with a special focus on continental free trade in Africa. And our analysis is really just describing the state of the world, given these existing tariffs and NTMs and given existing market conditions. So we don't model any of the chain reactions or responses you might expect to see from a policy change. We just look at observed trade policies. And so future work might be something like looking at a more complete simulation of the shifts you would see if you changed trade policy. Okay, so I'll walk through the theory that kind of lies underneath how we approach this analysis. So we start with the retail prices that a shopper might pay for foods in a marketplace. And so in this example, it's bread. And that retail item might be made from an imported commodity, such as wheat, and that has the world price shown there, PT. But then on top of that world price, there's the additional cost of compliance with trade policy. So although the price of wheat is at PT when it's still on the ship in the city where it's being imported, then the costs of NTM compliance and tariffs have to be paid. And so that gets added on top. And once the wheat leaves the ship and enters the importing country, we've reached the domestic price, PED. So then by extension, we can subtract that same additional cost of trade compliance from the retail price to get an estimate of what the retail price would be in the absence of those trade barriers. And then once we have that framework in place, sort of as Rachel described, we calculate the baseline cost of a healthy diet using the observed prices, which are affected by the trade barriers that do exist. And then we calculate the theoretical cost of a healthy diet using prices net of trade barriers. And then finally, we can look at the estimated share of the observed diet costs that are due to the existence of those trade barriers. And then, so just theoretically, the extent to which trade costs actually contribute to the cost of a healthy diet depends on, first of all, whether the items that are selected into that least cost diet are imported or made from imported commodities. And then secondly, whether there are meaningful trade costs associated with those imported commodities. So whether tariffs and NTMs are actually assessed on those commodities. And so a huge part of this project involved identifying and then linking together all the data that we needed to fill out each part of that framework. So we use retail prices from the International Comparison Program. Then we estimate import prices or unit values using the value and quantity of traded commodities from FAO. And then those traded commodities are matched to the retail items. We convert everything from kilograms to calories using nutrition composition data. And then finally, we link the import data to trade restrictions, the tariffs, and whether NTMs are imposed, as well as estimates of the actual dollar amount equivalent or the percentage of value equivalent associated with those NTMs. And so we end up with this big data set of retail and import prices and trade data across 144 countries. And so this is just a quick example of what happens in each stage of the analysis with the example of Nigeria. So you can see that tariffs are responsible for about 11 cents per day of diet costs. When you look at the baseline diet cost versus the without tariffs diet cost. And so what that's due to is this shift with milk, where the cost of milk is lower without tariffs, but the same type of milk is still selected. And then also this change for beef, where beef with bones becomes slightly less expensive. And so that becomes one of the animal source foods that enters the diet, because now minced beef isn't the best option. And then similarly, if we look at what happens without non-tariff measures, peanut oil becomes slightly less expensive, and so that replaces palm oil in the diet basket that's selected. And so then when we do this for all of the foods and countries in our data set, we find interesting differences across regions of the world and then across the healthy diet basket food groups. So you can see the contribution of NTMs it's variable, but it's fairly high compared to the cost of tariffs. That being said, the tariffs do make a meaningful contribution in these particular regions where it's noticeably higher. And then we also find that though still a relatively small absolute value in terms of percentage of diet costs, tariffs do constitute a larger share of diet costs for vegetables and animal source foods. And that's basically true regardless of the level of national income for different countries. So this exercise of connecting the least cost diet calculations with trade data reveals some interesting new insights. We find that the domestic value added turns out to account for 80% of retail prices and about 5 times the unit value of the imported commodity. So the price at the border, the unit of the imported ingredient. Most retail items in the ICP data set are importable. So can be matched to something that is imported in that country. And about 40% are subject to tariffs of some kind. And the documented trade restrictions are especially high in low and middle income countries and for vegetables and animal source foods. But at the same time, the cost of trade barriers turns out to account for a quite small portion of diet costs at around 20 to 2%. And this is probably because we've already reduced or eliminated many tariffs around the world. But it's also true that non-tariff measures are quite poorly understood, especially at the very detailed commodity level that we would want to have for a more nutrition sensitive analysis. So the estimates that we used in our study are quite rough and don't capture as much detail as, for example, the tariffs do at the level of specific commodities. And so to conclude, increasing access to imports is clearly of key importance for food systems, but at the same time, retail prices are driven by domestic value added rather than by trade costs.
Wonderful, thank you. And you might have noticed that I introduced Leah saying that she had a study of changes in food ever since 1960s. And that was entirely my mistake. Each student has multiple projects. So and my head spins to think how, what a diverse set of things we are covering when we unlock the potential for retail prices to reveal something about the state of the food system. And we promised you work on sustainable diets. So we'll have Elena talk first on linking item prices to environmental impacts. And then we'll close the loop at the end with Ash's talk on how climate change and extreme weather relates to food prices.
Thanks, Will. Hi, everyone. I'm Elena. I am also a PhD candidate here at the Friedman School at Tufts. And I'm going to talk a bit about some of my research looking at whether healthier, more environmentally sustainable foods are also more expensive. So we know that what we eat has very large impacts on the environment. Food systems are key contributors to a lot of the environmental crises that we're facing, such as climate change, massive biodiversity loss, water scarcity, and pollution. So reducing the environmental impact of food systems is really key, both to the health of our planet into the future and to our ability to keep producing and consuming healthy diets now and for future generations. And then, of course, we also know that what we eat has very important impacts on our health, and our food systems are linked to some of the key health and nutrition challenges that we face globally. So we hear a lot of talk about addressing these issues by shifting to more sustainable diets across multiple dimensions of sustainability, but changing what people eat is actually really, really difficult. And one key reason is that there's a lot of other drivers of food choice. When people are making decisions about what they want to purchase at a grocery store, health and environmental sustainability are typically not actually at the top of their list. And as we've been talking about today, price is a really key driver of what people choose to eat. And from research on this team, we know that many, many people around the world cannot afford to consume a healthy diet. And so knowing that, how can we expect that people will then choose to eat healthy, environmentally sustainable diets? And is it reasonable to think that that can happen? And we often hear this narrative, especially in popular culture, that eating environmentally sustainable foods is really expensive. And if you go to your grocery store and you look at labels indicating environmental sustainability, this might be reinforced because you'll probably see those labels on premium expensive products. So one thing I'm really interested in my research is to use retail food price data from around the world to dig into this issue and look at whether healthy environmentally sustainable foods actually are more expensive across countries. So to do this, I combine data from a few different sources. I'm using the retail food price data from the World Bank International Comparison Program that Rachel and Leah both described to us. I'm also using environmental impacts that were published in a paper from 2021 that looked at carbon footprint and water footprint per kilogram of over 300 food items. And then I'm calculating the nutritional quality of foods here using the Food Compass score, which is a nutrient profiling system that is intended to look at the healthfulness of food items across 9 dimensions. And this was developed by a team here at Tufts. So I'm going to share some of the results just looking at retail food prices and environmental sustainability mostly. So here the top of the line finding is that foods, when we look at retail food prices globally, foods with higher environmental impacts tend to be more expensive. So in other words, foods that are more environmentally sustainable tend to be less expensive. But there's a lot of variation between different types of environmental impacts and between food groups, and then also within food groups. So I'll dig into that a little bit. Here on this slide, I've divided the foods that we have retail food price data for in the ICP into 6 key food groups. These are also the healthy diet basket food groups that Rachel described for us a few minutes ago. On the y-axis of each of these charts, we're looking at price per kilocalorie of foods. And so here I'm comparing the green distributions, which are the prices of the foods in each food group with the lowest carbon footprint, to the orange distributions, which are the price per kilocalorie of the foods in each food group with the highest carbon footprint. So you can see that within each food group, the foods with higher carbon footprint tend to be more expensive. but the magnitude of difference varies between food groups, and there's a lot of variation within food groups in how much different foods cost. And then the story is a little bit different when we look at a different type of environmental impact. So when we look at water footprint, we see that for some food groups, like the vegetables, legumes, nuts, and seeds, and oils and fats shown at the top, foods with higher water footprint, and those are in the orange distribution, tend to be more expensive than foods with lower water footprint. But in other food groups, there's really very little difference in price by water footprint. So we find that generally environmentally sustainable foods tend to be less expensive, but there's a lot more to learn in this area. So of course, carbon footprint and water footprint are just two measures of environmental sustainability. There are other ways to measure these impacts. And then of course, we're not looking at other environmental impacts here, like contributions to biodiversity loss or land use or many other ways that food impacts the environment. Also, using the data set of environmental impacts that I'm showing here, it's very difficult to distinguish between different types and locations of food production. So for example, I'm often not able to distinguish between foods that were grown in organic production systems versus conventional production systems, or foods that were imported versus grown in the country where they're consumed. And that definitely would make a difference to some extent in environmental impact. And then, of course, other characteristics of foods matter a lot when we're thinking about sustainability, like nutrition. So in extensions of this work, I'm looking at nutritional quality and price of foods, and then other characteristics of foods as well, such as how they're processed or how long it takes to prepare them in the home. So it's just a preview of this work, but as Will said, if anyone is interested in this or is working on similar research, I'd really love to hear from you. Thanks so much.
Fantastic. And we're doing well on time, so we'll have a good opportunity to chat a little bit after Ash's presentation.
Great. Hi, everyone. Thank you so much for being here. I'm Ash Venkat, another PhD student in the Food Prices for Nutrition team. And today I'll be talking about supply chain resilience to extreme weather. So I wanted to start by sharing a very excellent graph from this review by Davis et al. And as part of this review, they reviewed a lot of literature on specific environmental shocks, where they occur in the food system throughout the supply chain, and which commodities have been studied. And they find that climate shocks to production are especially well studied, but other parts of the supply chain, such as storage, processing, and retail and markets, have not received nearly enough attention. Even within production shocks, we find a lot of emphasis on staple grains and cereals, particularly the top three cereal crops, maize, rice, and wheat. And we actually see very little research on climate shocks to nutrition-sensitive food groups, such as fruits and vegetables and animal source proteins. Finally, among extreme weather events, we see that floods and temperature extremes are pretty well studied, but we see very little research on other shocks, such as storms, earthquakes, diseases, and other shocks. So I provide this background to show that today you've heard a lot of examples about how retail prices affect diets, but research bias towards commodity prices and staple crops across, all of our domains really means that we have large gaps in our understanding of how each of these shocks affects households and diets. And there are lots of national and international retail price monitoring systems, and we've only recently begun to analyze the vast amounts of data available on retail prices and glean programmatic insights here. So the objective of this paper was to quantify the relationship between a suite of atmospheric shocks and how they affect retail food prices. So the suite of shocks that we studied are floods, droughts, heat waves, cold spells, and storms. And I'll describe the data sources in just a minute. But the fact that these retail price observations derive from early warning systems is particularly important because these systems provide a lot of rich data in poor countries that are often less, have sparse data access. We also partition our analysis by food groups for several different types of markets. So we look at rural-urban differences, and to some extent, we look at changes over time by looking at lagged events by 1 and 2 months. So here's just a brief overview of the methods. We start by compiling our data from 3 global early warning systems. So the sources are the FAO GIUS, the USAID FuseNet, and the WFP VAM databases. Following what you've heard described already, we adjust for inflation and then use World Bank purchasing power parity estimates to convert all prices into 2017 US dollars. And then we match every commodity and item in our data set to food composition tables to derive our outcome of in units of 2017 US dollars per 1,000 calories. In parallel, we also match market locations and the month of price observations to remote sensing data sets to derive our measure of shocks. So for floods and droughts, we use MODIS temperature and CHIRPS precipitation data sets. For heat waves and cold waves, we look at TERRA climate, maximum temperatures or minimum temperatures. And for storms, we look at the NOAA IBTRAX database. And by matching each of these data points in space and time, we're able to create constructed measures of whether a shock occurred during this time in a particular location. And we use different thresholds to define each event, which are of course listed here. And finally, we look at market locations matched to the DEG-URBA dataset to define whether the market was located in an urban area, a rural area, or kind of a transition zone between these two. So here's a quick look at our data set. We have about 1.3 million monthly price observations in over 2,300 markets in 71 countries. And you can see the map of market locations. There's an emphasis, of course, on food price monitoring in low and middle income countries, especially in Africa and Asia. The figure on the right provides a heat map of the number of markets which observe each of these events. Now, because our markets are kind of spread out around the world, we're not really able to see temporal clustering kind of along the y-axis, but we are able to see compare across events. And you'll note that heat waves are the most frequently occurring shock in our data set. They occur in about 78% of markets, whereas storms, because they're geographically and temporally concentrated, we only observe them in about 8% of markets. We then utilize this data set to implement a split sample OLS regression with fixed effects across each extreme event, urban category, and food group. And in doing so, we can develop graphs like this. So I'll first explain how to read this graph, and then we can dive into some of the insights. So in each of these graphs, the x-axis represents the % difference in price, and the colors represent different food groups. And a legend for that is kind of shown to the bottom left there. Lighter colors, and you'll see kind of each food group has 3 kind of colors in each graph. The lighter colors represent lagged extreme events by 1 or 2 months. Values greater than 0, so values that are to the right of the vertical red line there, represent supply reduction from greater spoilage, ineffective storage, or impeded access to markets, for example, for wholesale traders. Negative values, or values to the left of the red vertical lines, indicate demand reduction from wage losses or impeded access to markets for consumers. So I recognize that's very, very complex. So I'll break it down into kind of a group of overall insights. And I'll start with the good news is that we observe that a lot of results are statistically insignificant, which is great. It confirms our null hypothesis of no effect, or that supply chains are actually very resilient. And you'll see that because confidence intervals kind of cross the red vertical lines there. But we do see some exceptions, and I'll start with kind of the handful of stories that emerge now. First story that we see is the supply constrictions of breads and cereals after droughts in sub-Saharan Africa. And you'll see that because the values are positive and we're looking only at the yellow points here. The magnitude of these effects is fairly small. So we see the effect is about 5 to 6%, but they do affect both urban and rural markets. And when you know that this food group comprises the largest calorie share in poor people's diets, you can start to see potential issues. However, we see the opposite pattern after floods in sub-Saharan Africa. Now we see a demand reduction, and you can see that because the estimates are negative. And demand reduction means that people are shifting away from breads and cereals. And because the nature of floods, this likely means that people can no longer afford staple foods, indicating potentially worsening food insecurity following floods. We might also observe different patterns specific to, rural or urban places or in specific geographic regions. So for example, in South Asia, we see a sharp supply reduction of fruits and vegetables after floods. large confidence intervals that you see in the green dots here are telling us that the underlying distribution of values is fairly large. So there might be underlying volatility in this response or even regional differences within rural areas in South Asia that are contributing to this effect. And finally, in cities in East Asia and the Pacific, we see supply constrictions in urban markets after storms. And this is somewhat surprising because we might expect cities to be more resilient than rural areas because of improved infrastructure and better connectivity. But we still observe kind of a 5 to 8% increase in fruit and vegetable prices that we don't observe in rural areas. And of course, all these results taken together, the food group, the rural, urban, and the event-specific distinctions are important if you're a policymaker and you're trying to figure out how best to support diets after each of these events in each of these particular contexts. So in general, we observe that supply chains are very resilient to climate shocks. We see some instances of vulnerability, but we must keep in mind that these are net effects. We're only able to observe the net effect of lots of different supply and demand forces that are playing out at various scales. And the local, national, and international contexts and dynamics are often very relevant to the discussion. We also see that all shocks do not affect price in the same way or possibly in the same mechanism. And policymakers should account for all of these different pathways from event to price to design effective interventions to protect diets in the face of climate change. So I'll stop there. Thank you so much.
Wonderful. And that's a great slide to end on in terms of the funding for all this work. Comes from primarily the Gates Foundation and the UK government, also the FAO itself. And we have just a couple of minutes before 10 minutes of when some people will want to switch to another session, but we can actually stay on all the way until 3 if anybody wants to stay. And we can respond, after this event as well. So unlocking the potential of food price data has been just an enormous lift. When you hear the stories after the research has been done, it all seems, at least to me, like pretty simple. Like you've got a story, it's super clear. But Ash and Rachel and Leah and Jess have worked so hard to have these data matched in each of the research questions, to answer each of the research questions you've heard about. So this is far from exhausting all the research questions. It's just the beginning, I think, of understanding how retail items differ from wholesale commodities. You know that there's probably 20 or 30 agricultural farm products that dominate the food system. But in any given market, there's 20,000 items, and we're usually working with a subset of a few hundred at each location.